Hello, this will be our sixth video, Polymer 6, and in the previous ones we've done an awful lot to introduce polymers, but actually we've introduced a lot of much more general concepts than that, and we'll use those as we go through the course. I thought now might be kind of a convenient time to recap a little bit about what we've done. We began by reviewing organic chemistry. For some of you it was a review, for some of you it was quite new. But that's okay. We don't need to have it in enormous detail. You'll be fine. We talked about the enormous scale of polymer production. We mentioned the difference between addition polymerizations and polycondensations, which are now known as chain growth and step growth respectively. Then we had some fun pushing electrons around. We showed how the free radicals initiate and propagate the chain growth of polystyrene, and then for an example of a polycondensation or step growth, we did a little bit with nylon. I mentioned that when you do polymerizations, you do not get all the same sizes. And that's one of the foibles of being in polymer science game. And chemists work awfully hard, and chemical engineers too, to reduce that size distribution and make narrow samples in some cases. And in other cases, they really want them broad. But in any way, we need a control over that. We talked about the molecular weight distribution parameters, Mn, Mw, and so forth. We mentioned a little bit about how molecular weight averages are measured by osmometry and light scattering, and just in passing a few other techniques, including a calibrated technique or secondary technique called gel permeation chromatography, or GPC. We talked about biopolymers and gels. We talked a little bit after that about covalent gels, and we discussed such things as the various, the impossibly large number of conformational states that even a modestly sized polymer chain can enter into. It's really amazing that this happens, and nevertheless we can measure sizes of these things either by radius of gyration or center of mass radius, or by the end-to-end radius from one end of a chain to another. And we even talked a little bit about fractal dimensions. So in the process of doing all of this, we've learned a lot of stuff about polymers, but also a lot of stuff about material science in general. We even mentioned a little bit about diffusion and viscosity and viscoelasticity. So this has been kind of a watershed sample for us, okay? And we're not going to be able to cover all of these topics, but we covered some meanwhile, so it's okay. Let's see if I can get this thing to go. And let's actually break out and go more quickly to where we are now. We are going to talk today about crystallinity in polymers. And the first thing you need to know is that it's an amazing thing that it can happen at all. If I'm a polymer chain and I've got, what did we say last time, 3 to the 5,000 possible solutions, and that turned out to be maybe 10 to the 2,500 possible conformations. What the heck do I need to be in a crystal for? Give up all of that entropy to be into some sort of crystal. But they do. They actually do form crystals. And I love the idea of introducing you to crystals through polymers, because it's a kind of a complex crystal, but it drives home the point right away that crystals is not just about what happens to the atoms in aluminum and copper and what happens to the atoms in calcium fluoride and other simple crystals, okay? Crystallization happens, and it has enormous consequences for all sorts of materials and even very large molecules. including proteins and synthetic polymers, can form these crystals. It's kind of amazing. Equally important for synthetic polymers is the amorphous state of polymers, which is sometimes called the glassy state. And this also matters in other materials, ceramics. So again, our time spent in this chapter introducing concepts through soft materials, including, I forgot to even mention that we introduced Arrhenius law. Through these soft materials, will pay handsome dividends when we get to more hard materials, the metals and the ceramics. Okay, so it's cool. What is a crystal? Well, you can go to a dictionary and find that. The Oxford English Dictionary is a good example of a dictionary. It used to be this huge giant book. Now you just Google it up. And it's probably the definitive dictionary of all, because Oxford is a place of letters. And seems like it comes from ice. Okay, so one of the first crystals that people knew about was ice. And ice is hard, but it's also clear. And we get the notion from this association with ice and other minerals, think of topaz or diamond or other things, the gemstones that are known to be crystals. And you'll see that, it's often thought that they're clear. And we even have words like crystal clear, okay? So, this definition doesn't really cut it for us. In fact, here's definition 2, the standard type of clearness or transparency as in crystal clear, okay? So if we look at some polymers, these are some commercial polymers, and these are called pellets, okay? Polymers are produced in factories and they're chopped up into these little pellets, which then go into great hopper cars on rail, and they go to various plants like milk processing plants for making milk jugs and stuff like that. But it's often in the form of these pellets because that's convenient. You can get a great big bin of those to sort of flow through a hopper and then into an extruder and so forth. So you can process these pellets. They almost flow like they were a liquid, but of course they're not. They're just a bunch of solid pellets. Okay, they're like a sand pile. Okay, but the main point here that I want to point out is that they're not clear. Okay, right? Polymer crystals are not clear. Well, I could make the same argument. I could say I could grab some salt in my kitchen and show it to you in the salt shaker, and it's white, not clear. But if you were to, make a giant crystal of salt, sodium chloride, or even look carefully at those small crystals, one of them, you'd see that it is clear. So apparently inorganic minerals, often make clear crystals, and polymers often don't. And this has to do with a problem that polymers have when it comes to making crystals, which is that how do you pack all those chains into one little spot like that? But I'm kind of getting ahead of myself. Notice that there are 3 various sets of pellets here. And I've shown over here on the right 3 different polyethylene. These are all polyethylene. Polyethylene comes in like a million different grades, okay? Any commercial polymer. I think I counted once for polystyrene, and there was something like 80 different grades of polystyrene that you can buy. Different molecular weights, different other things, some of which we'll talk about in a little bit. But this one down here at the bottom where I'm pointing now, that's called high-density polyethylene. And notice that it's pretty much a straight line. It's also called linear polyethylene. And it may have little stubby things coming off of it now and again. Okay? It's everywhere along here. It's CH2, 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 and then right where the little stubby thing is, it's CH, and then a little stub that is also CH2. Okay. And then there's linear low density, which has more of the stubby things. Okay. And then there's low density, just low density, and there's even very low density. And what you do when you go to low density PE compared to high density PE or even linear low is you add a lot of longer branches. So these longer branches make it hard for the chains to approach each other closely and to make very tight crystals. But we really still haven't really haven't talked about what a crystal is even anymore quite yet. So, but you can take my word for it that the other things being equal, the low density materials here are going to be more clear. It's the opposite. It's opposite world. Okay, from thinking about diamonds as or crystals as being crystal clear. And it shouldn't be such a huge surprise. Plate glass that you have in windows, that's not crystalline, but it's clear. So it's not only crystals that are clear, I guess is what I should say. Okay, so it seems like standard English language just doesn't cut it. Crystal clear is sort of a dumb thing to say. We should say glass clear. You know, glass is clear. And polymer crystals are inevitably cloudy because it's hard to get them really big. Okay, so the reason your salt shaker, if you were to take, let's see if I can get a pen out here, a giant crystal of salt. Oops. Pen. We'll let it be red. I don't know why red is the default color. Here is a giant crystal of salt, okay? It's like a big block of rock salt, a huge thing. Let's just say it's even, you know, like 5 inches big. It's not a huge thing of salt. It should be kind of something to see. That actually is clear. But when you put it in your salt shaker, so I'll try to draw a salt shaker. Okay. You grind it up into little salt bits so that you can get it onto your food. Those are small. Okay. And so the light goes into them and gets rattled around a lot, and it kind of comes back at you white in color. And so that's what happens with polymer crystals. They tend to make smallish crystals, which is actually kind of a useful thing. Okay, so let's push ahead to a definition of crystals, because we're going to need this, trust me, as we get to other things in the future. The OED, in its 9th, the Oxford English Dictionary, in its 9th offered definition, says this in the yellow, which is really not that great. So I rewrote it down a little bit, and I say, a form in which the molecules and their natural components regularly aggregate. That's just fun. We'll see another definition of crystals as we get into smaller crystals that we can more reasonably think about solving in a kind of quantitative way. So the understanding that you're going to get of crystals for polymers is fine if we define crystals as shown here, a form in which the molecules and their natural compounds regularly aggregate. Okay, so of course the molecules that we're interested in right now are very large molecules, and they do aggregate. And this is showing kind of the same thing that we saw in the previous slide. I just drew this one myself. Linear low on the left there, low on the right with more long chain branches, LCBs. And it's actually a really good question, how you actually determine how many of those LCBs are present. That is actually a research area. We were very fortunate a number of years ago to be involved with a company on that. And that was a lawsuit that between some very heavy hitters, both foreign and domestic. And the outcome of that lawsuit was favorable to the company I was working with and earned them about $1 billion a year in profits. Okay, so because they claimed that they had a method of making these long chain branches. And the competitors said, no, you don't. You can't do that. And moreover, you can't even prove that they're there. Well, with an enormous research effort, they did prove that those are there. So I'm telling you, getting this information is not easy, okay? But this is the information we have. Well, down here in the lower right, you see some of the kinds of densities we're talking about. They're significantly different. High density is 0.94 all the way up to maybe 0.97, almost the same as water, okay? But not quite. Very low density is, 13% lower than water. Water would be 1 here. So, there's a difference. And when you buy polyethylene, you actually buy these grades, okay? And there's this other parameter here that tells you a little bit about how they behave in molten state. You can melt all of these things, so you can melt the crystal just like it was an ice crystal. And once you do, it will start to flow. Okay? Sometimes polymers do something really interesting before they start melting. Okay, so we'll talk about that soon. There's a nice article. This is really nice. Some information about polyolefins from Miriam Ali Al-Mahadid. Hard for me to say. She works at Qatar University. You might be wondering what they're doing with polyethylene in the desert. It is now known how to make polyethylene comes from oil. It's now known how to make it even out of natural gas. And these countries know that have all the oil know that their time is running out. They have got to figure out how to make value-added products. They can't just keep selling us the oil because we're not going to need as much of it as we used to. They can make the oil into polymers, and they're putting huge efforts into this, huge efforts, and they have hired a number of people, and they pay them ridiculous amounts of money. It's amazing. Okay, so certain factors affect polymer crystallinity, and we'll talk about some of these. The size of those side groups, the little stubby things, the extent of the chain branching, how long they are, how many of those chains, a thing called tacticity. We'll spend some time with that when we get there. And, what's in the in the repeating unit in the first place. I've just been showing you so far polyethylene. And then there can be other kinds of bonding that occur, so hydrogen bonds can occur, other strongly polar interactions could be present. All right, so let's see. Here is a thing called tacticity. And we could imagine this to be polystyrene. It really has to not be, shouldn't be polyethylene. If all the R groups, see the R groups here? If all the R groups were H, if they were all protons, then we would have polyethylene. Okay? So that is tacticity is not really an option there. However, the little stubby groups that come off there could be in some form or other. So, we could say that we were dealing with styrene. So, and if it was styrene, R for styrene would be equal to if R was equal to methyl, we would have, this would then be poly, I should have put a poly there. We would have polypropylene, polymer of the year, We have tons of polypropylene. We are not just making it into, or we're not spinning it. We're not doing the spun fibers, and we're not doing the blown fibers either, blown polypropylene fibers that we need for masks. It boggles my imagination why we're not able to do that at a rapid pace 6 months into the pandemic, or 7. But apparently we're still not able to do that. Hard to imagine. But in any case, if we have an R group here that's different from hydrogen, they can be disposed in different directions. They can be oriented in different directions. So here, you know, at each carbon center, each carbon is at the center of a tetrahedron. And you see this one here is called isotactic. Iso means the same. So same tacticity for all the R groups. They are all pointing, as this author likes to draw, a little bit up and towards us, out of the plane of the paper. All of them are doing that. Okay? Regularity in the structure makes it easier to have regularity in a crystal. Makes it easier for crystals. Okay? So isotactic tends to crystallize. And I found this out the hard way, because I was trying to do an experiment back when I was a postdoc, and I wanted a polystyrene of a certain molecular weight to do the experiment, and I got it, and it would not dissolve. Polystyrene dissolves. It dissolves in acetone, it dissolves in tetrahydrofuran, it dissolves in toluene, it dissolves in benzene. There's a zillion different solvents that dissolve this thing. But I got this one, and it just wouldn't dissolve. And I got to the point where I thought it was somebody had taken a bottle and put some other thing in it. You know, the bottle said polystyrene. Or maybe they put something else in it. They put Teflon in it or something. I was really curious. So I actually went back and looked at the bottle carefully, and it was isotactic polystyrene. Okay? Where all these R groups are the same, and it was crystalline. And there is no way to get it to dissolve unless you heat it. Okay? And in fact, in the solvent I was trying to work with, I couldn't heat it that far. The solvent would have evaporated. So it really matters. This crystallinity really matters to how the polymers behave. There's also syndiotactic, and here the R groups are, you know, up and out, just like they were there. And then, wait, and then over here, here's down and out. Up and out, down and out. Up and out, down and out. Sounds more like a businessman's rocky road to becoming wealthy. Doing great, and now I'm broke. Doing great, and I'm broke. But this also is regular, and it also can crystallize. And then there's atactic. So, you know, hopefully you can convince yourself here that there's no particular order. This one's up and out, that one's down and out. Then over here it's up and out again, but now it's up and out yet again. See, it's not up and then out. It's not out and then, not up and then down. It's, you know, up and up. So kind of more random. And what controls how this, what tacticity you get is the catalysts, okay? Catalysts. Okay, so this is distinctly chemical, and so really what has to happen in these catalysts, in most cases, in many cases, is monomer has to come kind of sit on the catalyst, in many cases, and be aligned in a certain direction. The catalyst helps align it, maybe prise it open a little bit to make that transition state a little lower in energy. And when that happens, maybe the next monomer unit that comes in trying to react to that has to kind of align to sit down onto that in the right place. Okay, so you could think about this, about these polymers coming down on the catalyst as getting onto a horse, right? If you've ever ridden a horse, you know that you usually ride facing forward. You could get on the saddle backward, facing backwards. It would be a weird ride, but you could do that. Or you could ride side saddle to the, you know, you could sit on the saddle, side saddle, depending on what you want to do. But in any case, there's a choice how the molecule sits on the catalyst. So this comes right down to atomic level of science. Okay, this is a better picture of one of these things. The one on top is isotactic, up and out, up and out, up and out, up and out, up and out every time, and then it's up and out, up and back, up and out, up and back, up and out, up and back. So that is a syndiotic, and this one at the bottom here is meant to be atactic. And they show in this case some ball models, which are kind of misleading because the real volume here that matters is where the electrons are. So this thing is a lot blobbier than that. We think of this as being this little thing here. You can think of that as being a proton, but the mass of the proton is in one little dot, and the volume taken is taken by the electrons. Okay, so they're bigger than they would seem. On the right here is a picture of a more accurate picture of the conformation. As we discussed earlier, it's there's nothing that prevents a polymer from laying out flat like this guy, but it's rare. Okay, they rarely lay out flat in this conformation. They tend to rotate around these angles, just like we've talked about already. So you have bond rotations, and as soon as you do that, you get a kind of a messy leaking structure like that. But I can't look at that. My eyes grow weary trying to figure out what tacticity that is. Okay, so it's easier just to sort of lay them out flat when you're talking about it. This shows what I was just saying, that it's really about the electron volume. So in this slide, which I think also comes from that same Wikipedia on tacticity, it's a pretty good Wikipedia article. So it tries to show where the electrons are, the electron map of this. But it also shows that when a vital unit comes in, it really can, add facing forward or facing around the other way. So here is, head to tail. So let's say this is the head, okay, and then it joins with the tail. So this is head, and that's tail, and then it's heads, and the next one is tail. Now this one is head to head, and this one is tail to tail. So this can all be figured out, and all these things slightly affect the behavior of the system. And they're all measured. The way we find this out is by nuclear magnetic resonance spectroscopy. And it's the catalysts that kind of control this to a considerable degree. Okay, if we go back a little bit, let's see. Here I show a polymer zone. This is a kind of making a crystalline zone in here. There's a zone where they're all sort of lined up, and you could imagine those crystallizing. But other zones might not crystallize. And in fact, the thing about polymers is that it's really important in most cases that they do not entirely crystallize. Okay, some regions of them should not crystallize. So the regions that don't crystallize, depending on the temperature and some other factors, are either sort of like a melt, or they're sort of rubbery, okay, or they can be glassy. It just all sort of depends, but they're not crystalline. So here's a concept map covering all the solids that I could think of. They could either be crystalline or non-crystalline. Crystalline means ordered. An example would be diamond, okay, or a really linear polyethylene, linear high-density polyethylene. Or they could be non-crystalline, then we have choices, glassy, of words. We have glassy, amorphous, or disordered we can use to describe that. But polymers are often sort of down here. Parts of them are crystalline and parts of them aren't, okay? And it leads to an overall structure kind of indicated here. It's a pretty shabby looking drawing here. But in some zone here, the polymer chains are lined up. Okay, we'll just say that's lined up, and it kind of comes out there. A chain comes out. And over here, we'll say this one is light up. It doesn't matter how it's oriented to that one. We'll say that that one chain there kind of went into the crystalline zone. And let's see, let's make this one vertical. And I can say this one is made by this chain here, which eventually works its way out there. And another chain can come in here, and you know, it could even exit at that point, just join up there for a little while. So lots of funny things can happen. But the point is that you get these crystalline zones, and then in between them, you have all this floppy mess. Okay, this is this floppy mess in between them. And crystalline zones give you strength. Okay, so polymers have impact resistance. You know, they have a little hardness. But they have, and this is the real secret to polymers, they have toughness, okay? So I got my cell phone here, and I can plunk it like that. I mean, I can take this here plastic clock. I could probably throw it across the floor and nothing would happen to it. When I was a kid growing up, that would not be the case, okay? We didn't have plastic sippy cups. We had aluminum cups. And if you dropped them, they got dented, but at least they didn't shatter and get you all cut. See, the parent wasn't going to give you a real glass, because you would drop it and break it and then step on it in your bare feet and cut yourself, right? So they gave us aluminum cups, but now we would give you a plastic cup because it won't even dent. It can take quite a lot of abuse. I mean, most things that are plastic are really able to take a lot of abuse because of this toughness characteristic, and it comes from those amorphous regions. But the whole thing is held together as a solid, kind of by the presence of these crystalline regions. Kind of neat. All right, so I thought you might like to see some crystals. This is classic work from a guy down at Florida State a long time ago. And he is looking at a transmission electron microscope image of some polyethylene crystals. I guess it might be polystyrene, but I think this is polyethylene. These crystals were grown out of a solution, so they managed to get the polymer to dissolve in something. If it was polyethylene, that means they were using a hot solvent. Polyethylene does not dissolve in cold solvents. Okay, it just doesn't, because you have to break up the crystals to do it. And then they heat it up, and just like we heated the Jello in a way, and they heat it up and they cool it down, and lo and behold, they get these sort of crystalline structures in there. And you can even see, you know, this guy here is actually on top of that other one down. Goodness. I don't know what happens with mouses and Windows. It's on top of that other one, and you can see that there, you know, over here there's regions where you can look through several of these crystals. And so if you see through something in an electron microscope, you know that it is something pretty thin. So these are thin little leaves of crystals, okay? And I tried to draw them down here, showing a kind of lamellar structure where they go back and forth. So the crystal structures kind of go back and forth here. They may loop around here a little bit before they come back. And there's always a certain amount of debate, you know, like how long they can come back and then go over here and come back in there, right? And their ability to do that depends on how stiff the chain is, how much time you give them, and stuff like that. Okay? So this is a polymer, whatever it is, it's crystallizable. Some polymers really have a hard time to crystallize, some just don't at all. All right, so the lozenges, I'll call those things that we were looking at, those little thin things, I'll call those lozenges. There are other ways, other motifs of crystallization, such as spherulites. And usually you see these in a polarized light microscopy image. Okay? And so we maybe talk about that just a little bit here in a minute. Yeah. zoom ahead here. I thought I moved that slide, apparently not. This is a picture of a light wave working its way through space, okay? And light is a combination of electromagnetic wave and a electric field wave and a magnetic field wave. And we kind of mentioned this before. And this thing here is the Poynting vector. I think we mentioned this when we were talking about, wavelengths and stuff like that. All right, so those two are at right angles to each other, the electric field and magnetic field. They're sort of at right angles to each other. Okay, and I think in this next slide, I show you a little something different. In this case, both of the waves that you see are actually electric fields. Okay, and what happens inside of a crystal is if light comes in, it will get split into two different electric fields. One is called the ordinary ray, and the other is called the extraordinary ray. And one is slightly longer wavelength than the other. And so they both have the same frequency. If you start launching a wave, there's nothing you can do to change its frequency. But you can change its wavelength. So the longer one goes farther, and the shorter wavelength goes not as far. So the longer wavelength gets a little bit ahead. And you can see that at the end here, by the time they come out, one has gotten a little bit ahead of the other. And that leads to a phase shift. And it actually rotates the net direction of light. Okay, so at the very beginning here, because I have I went back and got a better pen, hopefully. At the very beginning, here is the electric field of that red wave. And at the beginning, the red and the blue are almost in phase. Okay? So at the very beginning, those are almost at the same phase. And I could draw, so I'll do green, the net polarization of the light, the net E field, the electric fields add. Okay? So I would have, the net effect would be that the electric field is kind of in between the two. As we exit the sample, at the exit, you see that it's a slightly different situation. I'm now adding, there's no amplitude here at this point, and I'm adding a field here. If I go back to I'm adding a down here, and it's a little bit on the short side here. See, it's not quite there yet, right? So I'm adding those two vectors, and it is not exactly in the middle anymore. See, this green was right in between them, and now when I sum them together, it's not going to be that way. It's going to be sort of like that. Okay. So, in fact, the polarization of light gets changed as it goes through a crystal because the extraordinary ray and the ordinary ray have different speeds. So, when we look at a polymer, one of the ways that we often look at them is in this thing called the polarizing light microscope. And what the polarizing light microscope does is, here's our sample. If I get the color here. Our sample is here. Oops. I guess it's labeled. The sample is the yellow thing containing the crystals. And we have the polarizer, the electric field, is set this way. Okay. And then we have the light is coming this way. Light is coming in this direction. So this is our Poynting vector, S. Okay, and that's our initial polarization. And we can set this thing so that the only light that we see is light that's polarized that way. So if I put a non-crystalline material into the sample, what I'll see in that case is nothing. I'm sending in north polarized light, and I'm only looking at east polarized light. If the sample doesn't act and do something to the light, I won't see anything. I'll see blackness. And if you look at these images over here, blackness is pretty common. Okay, so in here, this zone here, this is an isotropic zone, or amorphous zone. Okay. However, it's not quite that simple. Okay, it's not quite that simple. If I look at these spherulites, this little guy here, which has a sort of Maltese cross going on there, all of it is crystal, but the light only gets out at these sort of 45-degree angles. Okay, so if I say, okay, so here's, vertical, here's horizontal, I'm only allowing light to come out here at 45 degrees. That's 45 degrees from vertical. And then nothing will happen at 90, and then I'll have light at 135 degrees. I'll have light again, and nothing will happen at 180, and so forth. Okay? And that happens because the crystals in spherulites are sort of aligned as you go around the sample. So different parts of them, of the spherulite, can grab the light in a way that lets some of it get through. And I'll try to explain that a little bit. Here's a better picture of them first. And these are spherulites that grew together. They started off growing as round things, and they kind of grew into each other. Okay? Social distancing apparently failed in this case. And the polymer chains up here, this person who drew this attempts to show that the polymer chains, the polymer chains really are aligned in kind of a radial way. So polarized light microscopy is how we do this, and there are some very good polarized light microscopy people in this campus. Mohan Srinivas Rao often teaches this course. He would be considered a world expert in this kind of analysis. I would not be. I do a little. We already looked at that. This is a better view of the polarized light microscope. Okay, and it shows that as the sample, the light starts off sorry, had to duck out a little bit again for a bit. It shows that shows that the light starts off as non-polarized light. Usually that's what microscope light sources do. And they put in this polarizing element, and they select out the east-west component, so the electric field is oscillating east-west. It enters this crystal. It gets split into an extraordinary and an ordinary ray. When it comes out, there's a path difference that results in there being a different polarization by the time it hits the analyzer, which is normally, in this case, north-south polarized. And so light will get through. Okay. These are some images that you can take on polarized light microscopes. That's sugar crystal. This one down here, I don't really know what it is, but it's spherulitic. Here's a beautiful Maltese cross in this one. Okay. And there are wonderful tutorials that you can watch from the microscope people. But I'd like to take a little time to explain what's going on with this Maltese cross, why we see this structure, okay? Because it's just vector addition in a sense. So our polymer chains are oriented as shown here, zigzagging, zigzagging, zigzagging. Let's look at this one in the horizontal plane here first, okay? And let's say that our light is polarized incoming, in this direction here, with our north, and our analyzer accepting light, that's east-west polarized, okay? So what happens in this case is that this crystal can't actually, the crystalline polymers that are in there don't really change the polarization of light. The light comes in north-south polarized, and it stays that way. So it doesn't get past the analyzer, okay? If I look at this vertically polarized situation here, now what happens is that the light may interact strongly with the incoming light, but again, it doesn't produce any component that has a it doesn't produce any transmitted light, has no horizontal component. Okay, no east-west component. So what really works is this situation here at 45-degree type angles and multiples of 45, 45, 135, whatever happens after 135, 225. So that one can interact with the light because it's, light is going up and down here. The incident light is driving electrons in the sample up and down. But going up and down in a structure like this also means going a little bit left and right because, the electrons have to sort of stay with their crystal structure. So the net effect is that the electrons are moving kind of at these diagonals. So I stimulate an up and down motion. And then, that results in a little bit of a left and right motion, which gets some light past the analyzer. So that's why you see these Maltese crosses at the 45 degrees. And this is just basic vector physics, okay? Right? So the light kind of grabs the electrons in the crystals, polarizes the electrons in a way, and we can compare that to the motion of this here Volkswagen. So here's a Volkswagen that's in the horizontal direction. It just sits there, right? Let's just say it's just sitting there. Somebody left the parking brake off, but it's on a totally flat piece of ground, just sitting there doing nothing, and it'll sit there forever. Okay? Now, if we could suddenly drop the Volkswagen off a cliff, it would definitely go down, right? But if it's lying on its door, it won't do anything again, okay? Right? So this is like the crystals that were organized this way, say, and this is like the crystals that are organized that way. No motion either way. But if I take this thing and I put it on a hill, it will roll down the hill, but rolling down the hill means rolling also left and right, right? There's a forces down, but the net effect includes also that we're going to move off to the right, right? And so we have a component that gets us, we have a force that gives us an action in another direction. Okay? And so that's really what's going on here. A little bit about sphere-like growth. They kind of grow from tiny seeds, and they kind of grow like that. You can also get these structures called shish kebabs, depending on how you cool the sample and then what they're in. These are important, different kinds of structure, and they process differently and so forth. And so I've kind of hit the end of this business on polymer crystallinity for right now. And I guess the main thing I want you to know is which one is the crystalline polymer, crystal clear one or the cloudy one, okay? The crystalline polymer is this one's, okay? That PMMA for a jet canopy was a miracle discovery in World War II to have those. To this day, PMMA, which you now see in your grocery stores everywhere, separating you from the clerk, is still pretty expensive material. Okay. Okay, so we're back. Now we're going to move ahead and learn a little bit about phase transitions in polymers and really in all sorts of materials. Your textbooks, the Schaefer, Saxena, Sanders text, actually has a statement in there that phase separation is not a thing in polymer science. That's nonsense. It just didn't get that right. There's lots of things nice about that book, but that's not one of them. Phase transitions are extremely important in polymer science, and we're going to introduce phase in this way, and then we'll come back to it. We'll need a lot more detail to understand the phases that happen in metal systems, because it gets pretty weird over there. Let's just talk a minute about simple melting and freezing. And it could be, we could be talking about ice or anything. It really doesn't matter what we're talking about here. The nature of the substance is not important yet. Okay, so let's make a plot. And the plot will show the amount of temperature we achieve as a function of time when adding heat. Okay, so if we add heat at a certain rate, we apply heat, we build ourselves a sample up here. We put an electrical resistor in there. The symbol for resistors is a zigzag. Okay, and we hook this thing up to a voltage source, a variable voltage source. There's a variable voltage source, and we can even put over here an amp meter, so we'll measure the amount of heat. Okay, and then of course this has to connect back. And I guess we could even tie it to ground if we want. Okay, so now it's tied to ground. And we put a sample here, and we're going to melt the sample. And we're going to adjust the voltage, and so that it's a nice steady resistive heating element going in there. And what we'll see is that the temperature will climb, of course. We're adding heat. That's not surprising. But if it's a solid, then at some point it will level off. Okay? And then it will start rising again. And this is, you know, the melting point here. Oops, this is, I wanted to draw that line that way. Sorry. This is the melting temperature. Okay. So, and what's going on is that it takes the sample a little bit of time before it can actually melt. So here we're solid, and here is solid plus some liquid. And then here is liquid. We finally did it. We finally got rid of all the solid. So that's a heating curve that we could get. There are also cooling curves that you can measure. So you can do this backwards. You can actually do it, the way done backwards. T, and then you can go this way. And actually, either one can be done. Time. Removing heat. Okay. So it's the same thing. Okay. This would be our T. Well, what will we call it? It's actually freezing, right? And then we get over here, and it is frozen. So this is liquid here. Liquid plus solid here. It's freezing now. And here it's all solid. Frozen, totally frozen over there. Now there are some finer points that happen here, particularly on these cooling curves. Oops. The cooling curves can have some weird things happening. So this was heating here. This was cooling. Some strange things can happen here while cooling. Okay. And one of them is this. The actual melting temperature, I'm sorry, I should have called it freezing temperature, but really, freezing temperature and melting temperature should be the same thing. Okay? So, it's still what it was. Okay? But in this zone here, say from, it should have started freezing, but it didn't. So in this zone here, we have a supercooled and you can do that. You can supercool a liquid. You can make that liquid be that should be ice, not be ice. I think we may have talked about this before. And so a lot of liquids will supercool because in order to get a crystal to form, it takes a little bit of time. Okay, and so all of this is happening, and the system may not be able to keep up, and may not be able to maintain equilibrium. So this is a non-equilibrium state. I'll just write non-EQ for non-equilibrium. And so once it starts to, the ice starts to form, then it, and you then get back to normal here. Now you have, super cooled liquid. You have a little bit of solid plus liquid here, and then eventually you get back to totally solid again, just like before. Right. So this is a difference between heating and melting. Generally, if you would like to know the melting temperature or the freezing temperature, they're the same. If you want to know it, you would generally be better off using the heating curve. Okay? However, if you want to know the amount of heat that's generated during the freezing, which is the same as the amount of heat that's absorbed when you melt it, then you're better off doing the cooling curve. Okay? So this one is better. And cooling curves are better for getting the, I'll say, enthalpy of freezing, which is minus the enthalpy of melting. Okay? So it depends on what you want. And the reason the cooling curve is better than the heating curve for getting the melting, the enthalpy, is because it all comes at once, okay? And your instrument captures it all at one time. The instruments that do this kind of measurements are actually called scanning calorimeters. Right? And they have a little bit of instability. So if you try to get the enthalpy on the heating cycle, you have to deal with the instrument's instability because it takes all this time in here. But a lot of your enthalpy comes right there when you're doing the cooling curve, and the thing finally goes ahead and freezes. It gives off a boatload of enthalpy right then and there, and the instrument is in one situation and captures it. So there's a little bit of art to making these measurements. Okay, so now we're going to deal with a different kind of phase separation. We're conditioned to think of phases as solid, liquid, gas. Some people include plasma, some people include liquid crystals. We could talk about glasses. One way to look at them is like liquids, but not moving. So, at least not moving very fast. This is a different thing here. This is two liquids, both definitely liquids. At least they're liquids at the beginning, but they have different compositions. So to do this, we have to introduce two-component liquid-liquid phase diagrams. Okay, so that'll be fun. So we'll go over here. We'll get a pen and on our x-axis, we'll write WB as our independent variable. B is one component, and A is the other component. Okay? And I keep hoping that I can color code these a little bit. Let's see if that works. So let's say B will be red. Okay? And A will be blue. Okay? So anyway, if we have WB equals 1, that means pure B. Okay? And WB equals to 0 means pure A, no B. So these, the other axis here is temperature. Okay? So this is altogether a temperature composition phase diagram. And we'll see these, okay? B and A can be almost anything. There could be, B could be benzene and A could be alcohol, right? Or B and A could both be polymers, different polymers. Maybe one is styrene, the other is butadiene. Could be that B is a polymer and A is some solvent for the polymer, at least at some temperature if it's a solvent for the polymer. Otherwise, this wouldn't be very interesting. All right, so these phase diagrams look like this. Sometimes they may look like that. And let's suppose that we label this temperature here T critical. What's critical about it is that above that phase, above that temperature, you don't have two phases anymore. Okay, so you have one phase up here. All right? And what it really means is that I can make any mixture I want. I can have all A's on this side. Since I'm not exactly right on the axis, I could try to add a B or two. A couple of red dots could go in there. I don't know if you can even see them. Doesn't matter. All right. Or I could add. Go away. I could add mostly B's. And I could be on the right side of this phase diagram, so it's mostly red on this side. Okay? Or I could have in the middle, you know, equal numbers of red and blue. So I'll put in some red in the middle. And I'll put in some blues there too. So I have sort of equal mixtures of them. But in any case, whatever my overall composition is, okay, my overall composition could be almost pure A or almost pure B or somewhere in the middle. Any way you look at it, I have a single phase, and what that means is that the whole system is completely uniform throughout its container. It's a liquid, so it has to be in a container. So I have a single, just looks like a perfectly nicely mixed system. If I lower, and this, let's say this happens at some, you know, above T crit. Below T critical, let's just pick one. Let's pick a value here. We'll pick, call this T2, okay? I guess I could have said, let me repurpose this T and say that's T1 there. And our general axis is just, you know, this is, okay, so this is our T1, okay? So T1 is greater than T crit, T2 is less than T crit. At T2, you have two phases, alpha and beta. As long as your overall composition is in between those values, okay? So here you would say, okay, just to use this notation, let's say this is our alpha phase. So this is W B of the alpha phase. And over here, this is WB of the beta phase. Now, if you, one thing to remember is that WB is just an indicator of the composition, but you have to specify the overall composition. You have to specify I'm 50-50 A and B. That's the overall composition. So let's pick an overall composition. I take every molecule that's in the beaker and I say count them all. I weigh them all because we're in weight fraction. I weigh them all. And I say the total weight of A is 50% and the total weight of B is 50% of the total weight. That would land me right here at 0.5 as my overall composition, and I would be right here. So that's a point. That's a point on the phase diagram. And at that point, the way to read this is that I have a single fluid of A's mixed in B's, pretty much like I've indicated there. Okay? Right? So if I keep that overall composition and lower the temperature, now my overall composition comes down to here, and I'm going to use a different symbol. I'm going to put a star there. That's my overall composition. I went straight down. But the system, if you give it enough time, and that's critical, if you give it enough time, it's going to separate into two phases, alpha, the alpha phase, and the beta phase. That's what it'll do if you give it a lot of time. Okay? So if this is our situation, that we have this overall mixture, I guess it's maybe 0.45 or something the way I drew it. If that's my overall composition and I've lowered the temperature, what I expect to actually see if I look into the beaker, here's a beaker, little pour spout there for the beaker, I guess. What I will have at the end of that will be B. All right, we'll just go with B. And then we'll have A on top. Okay. I'm going to assume that, for no particular reason, that B is a denser material than A, so that it sinks to the bottom. That's our equilibrium situation. That's how we would read this phase situation. Okay? So, well, the amount of liquids that you get varies, but I really want to focus right now more on what happens if, why it's this way. Let's say, why is it this way? Okay? What this is telling us is that if you give the solutions enough time, if you give the molecules enough time, an A molecule is just as happy in the alpha phase as it is in the beta phase. Okay? So let's say that our WA alpha here is our WB in the alpha phase here is 0.15. If we wanted to, we could say our WA alpha then is 1 minus 0.15 or 0.85. Everything in the sample counts for total weight, so the sum of the weight fractions has got to be 1. As I've drawn it here, it looks like WB in the beta phase, maybe 0.8. And WA in the beta phase would be the 0.2. So if I'm an A molecule, it says, okay, I like my neighbors, but I only like them in two situations. I only want to be around 85% other molecules being A and 15% being B, or, that's the alpha phase, or I'm just as happy as an A molecule to be in a neighborhood where I have 20% of my neighbors are also A and 80% of them are B. Doesn't matter to me. I'm happy with that either way. And this is actually, there is a way of expressing this that I want to introduce you to, because many of you are the kinds of engineers that deal with this a lot, and in liquid phases too. I want to introduce a variable called mu, and we'll introduce it for the A component. And what it is the change, the partial derivative of the free energy of the system with respect to the number of A molecules holding temperature and pressure constant. Now, I'm not sure everybody in here is in a partial differential, comfortable with these partial differentials yet, but it's okay. What this really is telling us, you don't ignore the funny notation, the weird looking D, the T, and the P on the outside, ignore all that. It's really telling us how the increment of free energy we get if we add a mole of A molecules. Okay? Right? And it varies. That actually varies depending on how many A molecules are already there. And this thing actually gets a name, and it's called the chemical potential of component A. And there is similarly a mu B. Like I said, don't worry about it. I often show you things that are a little beyond. Okay, so the condition for the condition that specifies what these alpha and beta phases are. How does the system know to make 15% alpha and 85%, 15% B in the alpha phase and 80% B in the beta phase? How does it know that? I don't know. Okay, it's a chemical, it's a mixture of chemicals. They know what they want to do. It's not like we get to decide this. Okay, that's the main thing you need to know. We don't get to decide this. This is what nature gives us. So, but we get to name the variables and try to understand. And these chemical potentials are really describing the desire of the system to be something else or someplace else. Okay? They're escape potentials. And you can escape to some other chemical, i.e., you can react or you can just escape to some other place, phase. Or you could do combinations of those. Okay, that can happen too. And if you're a chemical engineer, you'll figure all that out eventually. That's what you'll be doing. Anyway, we're really talking mostly about this escaping to a different place, a different phase, a different part of the system. And the condition for phase equilibrium, like I've drawn here, the condition for phase equilibrium is that the chemical potential of a component is the same no matter what phase it's in. Okay? So we could write that like this. Mu A in the alpha phase is equal to mu A in the beta phase. And it has to also be true, if it's a phase equilibrated system, it has also to be true that mu B in the alpha phase is equal to mu B in the beta phase. All right? So when the escape potentials are the same, a molecule that's in the alpha phase, an A molecule in the alpha phase, is surrounded mostly by A molecules. But it says, I don't mind, I can go over to this beta phase. I'm just as happy to be surrounded mostly by these B molecules. Right? Notice it doesn't go just randomly in between, though. It's going to be either or. Okay? So if I started a process, let's do a process. And let's actually start a process where we go from this point here at the top. It's in a one-phase system. And I start cooling the system. It'll start drifting towards these new phases. Okay? We'll do that. If I go right to the very top of the phase diagram, it'll do that immediately. If I don't go through the very top of the phase diagram, there's what's called the metastability gap. And the system can just kind of hang up for a while and do nothing. It can just kind of hang up for a while. So this diagram's getting a little crowded, so let me draw us a new one here. It won't take but a second. Make it a little bigger perhaps. T, W, B, 0 to 1. Critical temperature here. And it goes like that. There is another curve that can come in here. And it's looks kind of like this. Now this blue curve here gets a name, and so does our original black curve get a name. The blue curve is actually called the Spinodal. And the black curve is called the Binodal. Okay? So I just gave you the conditions that establish the binodal. Okay? The binodal is established by mu1 alpha. I'm sorry, mu A alpha is mu A beta, and mu B alpha is equal to mu B beta. That's our binodal curve. Right? I'm not going to give you the conditions for the spinodal just now, maybe later. But the difference is that once you get under the spinodal, okay, if I get under the spinodal, there's essentially no activation energy to phase separation. I'm just going to write phase sepin. Okay? So, and these two really should come up here and kiss at the top. Okay, they should really be, should have drawn that a little better. Okay, they touch at the top. All right. And there's a region in between here. This region is called the metastability gap. And it's the same whether it's left or right, doesn't matter. All right. So if I do paths, we talk about various paths. So I can start a path up here and start a path up here. And I start cooling the sample down. And as I told you, it will start phase separating. The question is, how far will it get? Okay. But it will start phase separating almost immediately, right? If I do another path, let's suppose this was, you know, I think we said 0.45 on the previous one, and we had a tick mark for our overall composition. We had a tick mark at 0.5. Let's suppose I do, you know, more like 0.2. Overall composition, now 0.2. More A than B. Definitely more A than B. If I come down here and I get this far, the system may just sit there a while and do nothing. Okay? It may just sit there for a while and do nothing. And it's actually waiting for the first little bit of new phase to form. Okay, it doesn't happen instantaneously. There's a sort of like an energy of activation that you have to cross to get over the hump to make the new phases. Now, if we're going to go, let's suppose we're going to go down here. Either way, we're going to go in that direction, we're going to go in that direction. We're going to go to our T2. If you give them enough time, both of these situations will lead to the presence of alpha phase and beta phase. It turns out that there is going to be, let's say this is a path 2. We'll call this one path. So if we do path 2 or path 1, we will get alpha phase and beta phase in both cases. And these phases, we'll describe them a little bit more in a bit. But just, you know, as a reminder, the alpha phase looks like, as I've drawn it here, maybe, I don't know, 5% of B and 95% of A, the way I've drawn it here. This is drawn a little differently than the previous one was. That's okay. That's okay. Okay, and then the beta phase looks like, you know, in this case, the beta phase looks like 90% B and 10% A. All this is by mass. Okay. So you can imagine what that looks like if I were to color code my molecules again, such that we had B as red. This is going to be mostly blue, sort of with a little red, so maybe a light purple. And this is going to be mostly red with a little blue, sort of more of a, I don't know what color that is. But anyway, we get the same two phases, but path 2 gives us more of the alpha phase. Okay. Right. Then path 1, and this goes by something called the lever rule, and we'll encounter it later on. Don't worry. So, but you do have both alpha phase and beta phase in both pathways. You get a little bit more of the alpha phase, relatively more of the alpha phase if we do the path 2. But the really key difference here is the structures that happen. Okay? When a system undergoes path 1, it goes underneath the spinodal. Okay? And this is going to be a spinodal decomposition. Okay? And path 2 is what's called nucleation and growth. And these are different looking structures, totally different looking structures. Okay? Which wouldn't matter. At equilibrium, the situation is the same. Okay? I have some of the alpha phase and some of the beta phase. The key thing here is that you don't always get equilibrium. That's the key thing. If you go through path 2, nucleation and growth, you tend to get structures that look like this. Okay, excellent. So I remembered to turn the record back on. My son was right. You only make that mistake once. Because I told him that, and he was amazed that I did that. And he said, you only do it once. Everybody does it. He's in the recording business. Okay, so what I want to talk about now is a little bit about the concentration profiles that pertain during these fluctuations and during these phase separations. Okay, and so if what we can do, we can imagine a system, a stable one-phase system. Let's imagine a stable one-phase system, and let's plot the concentration. Let's say the concentration of B molecules. So it could go from concentration of B. We have A and B mixed together. Could be anything. Could be iron and tin, or could be iron and aluminum, iron and carbon, whatever else goes in there. But mostly we're talking about polymers right now, so why not let it be polymers and solvent, or two different polymers. And the concentration could be 0, B, up to 100%. And my x-axis here is really going to be a spatial axis. It's actually somewhere a position in the sample, you know. So I got this sample. It's in a beaker, okay. And why don't we say that x direction is vertical, just to make life sort of unusual and different. But anyway, that's fine. So, you know, what I will find is that there is an overall concentration, okay? But I'm being careful to put in little wiggles because there is Brownian motion that causes there to be slight fluctuations in the concentration at certain positions. Now you can't see that unless you look with a really fine magnifying glass or something. You won't probably see that, but it's there, okay? And that's what I have in a stable one-phase system. Now, if I cool this down, let's say I'm cooling this down, what I might find is that I go into the metastable gap. So I cool this down, I go into the metastability gap, everything's good there. And but like I said, maybe nothing happens for a long time. Then after a while, a nucleus forms. So we're going to draw our first nucleus. This is the concentration of B. Okay? And what we're going to say is a nucleus forms. Well, how does it form? Okay? The system is waiting, you know, random Brownian motion. The molecules are sort of moving together, and they finally, two of them get so close together they stick. And they make two molecules together, okay? And then maybe, you know, some more come in, okay? And we finally get a nucleus. And let's suppose that, so we said this is 100%, this is 0%. And I think we had this alpha phase was going to be down here. I think we said it was sort of like 0.1. So this is going to be our alpha composition. And then we had the beta composition, was so closer to 90. So this is going to be the beta composition. And we're clearly at neither one of these. When we start out up here at the top, we're, you know, before we have any phase separation up in here, we don't have either phase. We just have the one phase region, okay? But here's the formation of the first nucleus. Here's what it looks like. Let's form like 3 nuclei. So now I've formed 3 nuclei, okay? And what I did is that I had this depletion here. So I took some of my overall composition, you know, this is the overall composition, CB, overall composition, and I grabbed a bunch of molecules out of that, and I used them to form this more concentrated phase up here at the top, okay? And I fully formed, I took that phase, and that's like fully formed. But now look, near that nucleus, this is a nucleus, near that nucleus, there's a depletion of the B molecules because we sent a lot of them into the droplet. We created this little droplet of something. And so we took a bunch of molecules from the surroundings and put it in there. So that means there's a depletion. So whenever the concentration, let's take this spot here, this is a particular value in this solution, a molecule that's, you know, at that particular position in space, a particular x-coordinate in space, that molecule is at a higher concentration there than it would be if it was down here where I'm isolating now. So these things diffuse down. This is just generally downward motion. I mean, they just sort of fall into this trap. Okay? So this is normal. I'll call it downward diffusion. From a higher concentration to lower. And that's what things do. I mean, if you don't believe that, get yourself some food coloring from your baking cabinet and drop it gently into a cup of water, and you'll see that it sort of slowly spreads, okay? Actually, that sounds like a different kind of diffusion than what we talked about earlier. Earlier we talked about diffusion, self-diffusion, and we said that's like the mean squared displacement divided by time. I think we hopefully just put in a proportion of it here. Okay. But there is another kind of diffusion which is very important, and this is called mutual diffusion. And it's really governed by fluxes. Okay, it really describes the flux. Molecules, particles, whatever. In response to a concentration gradient. That's what it does. And apparently I just cannot get any thicker here. Okay, and so we'll talk about that a little bit more. But we're right now, just right down here briefly, J, we can define J to be the flux of molecules past a certain imaginary window in space. So if I, scroll up here again, and I say, here's my X. If I was to zoom in on this thing here, I could sort of imagine a little zoom area in here. There's molecules, and they're fluxing through this space because they're higher concentration on the bottom than they are on the top. Let's just stipulate that that's how it is. So, here we'll put 2 molecules, and here we'll put, I don't know, a dozen molecules. The natural course of things is that this higher concentration is going to diffuse to lower concentration. Why? Because that's more entropy if it does that, okay? So that's called the flux. And it's actually, we could define it as, molecules per second per unit area. So, for example, it could be have the units molecules per second per square centimeter. Okay? So that's what flux is. And it turns out that that flux is proportional to the gradient in the concentration. So this sort of flux turns out to be D mutual times D concentration dx. And that would be right except for one thing. The sign has to be minus because it goes from high concentration to low. So this is actually, gets a name. This is actually called Fick's first law. And later we'll talk about Fick's second law. But right now, all we need to know is that it makes perfect sense. It makes absolutely perfect sense for, I'll color this thing red now if it'll let me. It makes absolutely perfect sense for this little molecule at this particular X value to diffuse down from high concentration to low. And when it gets down to the bottom of that little well, it sticks to the nucleus, which causes growth, okay? So what happens over a course of time, if I look at nucleation and growth, basically it will draw the whole thing out now in different stages. We'll say, okay, initially, let's say t less than 0. This is some beginning of the process. I'm still in the one phase region. So 0 time, and here's my X here, and here's my CB, here's my alpha, here's my beta. And it starts like this, little fluctuations, not doing anything. Okay? Then we cool it. In some systems, you heat it. In some systems, you apply pressure. Anyway, it doesn't matter. You change it. You initiate phase separation, and you get these spikes of nucleus forming, like we drew. Draw 3 just because we had 3 before. And then you wait. I should say cool into the metastable. I'll just say meta regime. Okay, so we cool into the metastable regime, boom, and we form nuclei, marvelous. And then we wait, and these nuclei fatten up. They do what people do over the course of time. Let's suppose the second two somehow coalesce even, okay? And now we only have 2. And then if you wait more, infinity time, this is supposed to be beta. If you wait even more time, you have a bunch of beta phase, which we decided was denser, so we'll put that at the bottom. And you have that. Okay? So that's nucleation and growth. Without really explaining exactly why, let's just draw the equivalent steps for spinodal composition. So this is nucleation and growth. The R's, nucleation and growth. Okay, spinodal decomposition is a different thing, okay? Instead of going up, forming a nuclei as it's fully formed, kaboom, you make a fully formed nucleus, the full composition is there, and then it just gets fatter. In spinodal decomposition, the trend, these are all going to be the same. Try to align these all. Okay. What happens is nothing. Here's the one phase region, so the same thing. So starts the same. What happens here is that you get sort of undulations. And notice that they're not fully formed. Okay? Nothing is close to the fully formed beta phase and fully formed alpha phase, just not there yet. And it turns out that this can be expressed as a bunch of sine waves if you want anything that has A structure that goes like that could be a bunch of sine waves, but it turns out one of them pretty quickly dominates the growth. And then what you start having is, let's just say that the sine wave is this way, and it starts growing like that. And what's kind of amazing about this is that if I'm a molecule, if I'm a molecule down here at this particular value of x, so take a particular value of x here, okay, and I'm a molecule there, I actually climb up the concentration to make that nucleus form, to make that new phase form. I actually get to diffuse up. And that's because I'm sort of being attracted by other molecules that are already there. I no longer want to be around. I'm a B molecule, damn it, I don't want to be around all these A's. I want to belong with the B's, and everybody knows the B people have more fun. So anyway, so it's actually kind of an uphill diffusion. It's sort of a weird situation. And but the end result is the same. Okay, so if we don't really get to equilibrium, it's a very useful thing, because then we have these sort of trapped structures, and you can see that if we stopped the process here for nucleation and growth, we would expect, as we drew a concentration profile across the system, that we have, nothing, and then these little spikes of stuff, beta phase, all of a sudden there'd be that. And if we did a spinodal decomposition and we got it trapped, or sometimes people say frustrated, it just can't get to the equilibrium condition, then we, instead of having those spikes, we just have these sort of smooth undulations, which sort of looks like worms or something, or spongy type structure going through the sample. So this next slide sort of shows that. This sort of frustrated phase separation. We can use that in all kinds of materials to make structures. It is most commonly used for polymers. It was actually invented, this idea goes back to a guy named Cahn, C-A-H-N, and it's often called Cahn-Hilliard spinodal decomposition, and these considerations of nucleation and growth versus spinodal decomposition go back to, I don't know, maybe the 1960s, or right around then. And if we trap, if we get frustrated at the nucleation and growth phase, we sort of trap little pools of beta, these little pools of beta that we're trapping in here, in a mixture of the alpha phase. Well, that could be useful. Maybe the beta phase has, I don't know, maybe perfume or something trapped inside of it. And so that would be a useful thing as we, as a surface wears down through natural process of oxidation or something, these little puddles would open up in the perfume, or maybe it's an oil or something for lubrication could escape. Contrast that with the spinodal decomposition, and you'll see that it's a different structure totally. So this is what I get. Oops. Let's see if I get it on. So this is the nucleation and growth type phenomenon here, and then these sort of islands there, and this sort of swampy, river delta type look, this sort of permeated structure is what happens if you trap a spinodal decomposition. Totally different structures, totally different properties. A lot of surface area in this spinodal decomposition, kind of this interpenetrated structure. Sometimes you can imagine taking one of these phases, say the blue one, and heating it up until it's sintered out, and then you wind up with this just open, porous, spongy type network. So this is a way of getting structure into polymers, which, as molecules, they often have this sort of no structure, just sort of flexible structure, but we've now seen that they can crystallize, and then the phase separation itself can lead to kind of structure. That's kind of a neat thing. And we'll see echoes of this in other materials. This is just a slide to point out that this sort of thing, this sort of frustration of phase separation also occurs in gelling systems. We talked about various kinds of gels, chemical gels where there are cross-links stabilized in here. And then here's a category of reversible gels. We talked about the collagen gel that we make for gelatin, jello. But here is a sort of a structure that's based on phase separation. Okay, so that can happen. So you can have this sort of permanent, and you can have it sort of transient. There's various ways to categorize these gelation processes.